All right. What I want to talk about in these examples, well, the first example is how do we deal with discontinuities? So we've got a derivative here. Let's go ahead and find the function y equals. So let's see, what do I know? What function has a derivative x? Well, x squared will have a derivative of x. X squared, however, will have a derivative of 2x, which means I need to put a multiplier of 1/2 there to get rid of that 2 when I take the derivative. And I know that tangent has a derivative of secant squared, which means this will be tangent of x, the antiderivative of secant squared. And I know that I need to add a constant. So let's see what we got here. Before I calculate the value of the constant, I want to take a look at this function because I know that I've got some vertical asymptotes here. And this function looks something like this, and over here it looks something like that. The details are sort of irrelevant. Um, but notice that the point 0, comma 3 happens to fall in here somewhere. Clearly, I mean, I guess I could narrow it right down to say it has to be right there on that function. Um, what this tells me is that I have a domain restriction of negative pi over 2 to pi over 2 for my solution. When I've figured out what the function is, it's only true in that domain because that's the only part of this function that goes through this point 0, comma 3. So very quickly, 3 equals half of 0 squared minus tangent of 0 plus c. 0 squared is 0. Tangent of 0, remember the tangent of a 0 degree is tangent of a horizontal line. Slope, that's also 0. C is equal to 3, which means that the function is y equals 1/2 x squared minus tangent x plus 3 for x, less than, negative pi over 2 less than x less than pi over 2. And this is important because this is not a true statement unless you put that domain restriction in. This function does not have that derivative and go through that point if you're outside these boundaries. All right, so my students, go ahead and do exercise 15. And when you come back, we'll do one more example. And the example we will do will be using the fundamental theorem of calculus. I am given a derivative, which is e to the negative x squared, and I am told that f of 7 is equal to 3. Now, it turns out we don't have an antiderivative for e to the negative x squared. We have no idea. There's no way to know. It's unknowable. Nobody knows. But what we can do is we can say, well, hang on a second. The function that has a derivative of e to the negative x squared is the integral of e to the negative x squared dx, because that's the fundamental theorem of calculus. The derivative of the integral is the function. The derivative of the integral of e to the negative x squared is therefore e to the negative x squared, so long as I am going from some starting point to x. So, fundamental theorem of calculus says that the derivative of this is that. Now, how do I deal with the initial value? Well, let's start by saying that when x is 7, this is equal to 3. So f of 7 is equal to the integral from a to 7 of e to the negative x squared dx. Except that I don't know that that's 3. Unless, of course, instead of putting an a right there, I put a 7 right there and add 3. I think we can all agree that that is equal to 0. which means that f of 7 is equal to 3, which means that my function f of x is the integral from 7 to x of e to the negative x squared dx plus 3. Now, got to be a little bit careful because I just made one of the classic blunders. No, not fighting a land war in Asia, but I can't have the same variable up here and down here, so I need to change that to a t. But hopefully we can all agree that if I plug in x equals 7, the integral from 7 to 7 is 0, which means that this has an initial value at 7 of 3, and the derivative of that integral is the function evaluated at x, which means there is the solution using the fundamental theorem of calculus. And in fact, like I said, this is the only way we can do this one. We don't have an antiderivative for e to the negative x squared. It's just one of those weird functions. But if we want a specific value, now we can jump into our calculator and we can just go ahead and say, we'll just plug that into the calculator and we'll find a value of the function at any given point. All right. My students, go ahead and do exercise 21. I'm going to end this video here, and when we come back, we will start getting into slope fields. Thanks for watching, and hope you learned something.